Yeah. And this is an error that's not supposed to happen, but it seems to happen every once in a while. So the exams, I guess, will have to be regraded, and I suppose that's going to cause everybody's grade to go up by, what, 20%? Not 20%, 5%. 1 out of 20. 20% sounds better. So anyway, yes, there was a mistake on the exam. One might call it a typographical error.
What question was it?
It was the one where you were given delta G at 2 temperatures. I was afraid someone would say that. Well, now you learn, good test-taking strategy. Good test-taking strategy. If you encounter a situation like that, don't spend the whole test time trying to resolve that problem.
No, I finished the test and then went to it.
Move on. See, there's a good strategy. Do the rest of the tests, move on. All right, anyway, that's that. All right. So I want to quiet. Okay, so last time I derived this equation called the Nernst Equation. Nernst Equation is named for a German physical chemist, Walther Nernst. He lived in the late 19th, early 20th century. He won one of the very earliest Nobel Prizes in chemistry for the theory that led to the Nernst equation. And again, I think I mentioned this to you, that one of the driving forces behind all great scientists is massive and insatiable ego. I told you that, right? So a great scientist, I think to excel in almost any career, you want to be the best surgeon. You want to be the top veterinarian in wherever. There's a lot of ego in that for to be successful in any chosen profession. I guess ego is involved, but scientists are particular egomaniacs. As egomaniacs go, we're way up there with politicians and actors, I guess. So we would love to be immortalized, memorialized, remembered forever. Walther Nernst, who died over 100 years ago, not over 100, around 100 years ago, immortalized, memorialized, you learn about him to this day. So congratulations, Walther. You're Nobel laureate, you. And it's important because, as I say right there, this equation allows you to calculate the voltage of any electrochemical cell. And it works. Meaning, you think of some cell in your head, you assemble that cell, you get yourself a voltmeter, you measure the voltage of that cell. It will be what you calculate from the Nernst equation. So fact, theory, and experiment agree beautifully. And I did my graduate research at the University of Arizona, an almost prestigious, almost West Coast school. I did my graduate research on a project that involved a variant of the Nernst equation. So, very important equation for me. And we derived it from this equation that we worked with earlier, when we studied thermo, which you all must really know the thermo because you did real well on the thermo quiz and real well on the thermo exam, so you must know your thermo. And by a simple dividing through, so if we consider, again, I want to consider this Danielle cell. Just call it X molar, salt bridge, copper 2 plus, call it Y molar, copper, for which we have the handy dandy situation that the anode reaction, written as a reduction, is that, and the cathode reaction, written as a reduction, is that. So for this process, it's very clear that N equal 2, where N has units of moles of electron per mole of whatever, zinc, or mole electron per mole of zinc 2 plus. But what we said is that if we divide that equation by N and by one of my favorite constants, F, the Faraday constant, and that, let's return to Faraday in a second. What's Faraday constant? We'll give you the number. It depends on who you ask. This is a number I memorized as a graduate student, and it's stuck in my head. I think your book uses a slightly different number, like 96,502 or something. I can't remember. But coulombs per mole of electrons. So remember, coulombs are quantity of electrical charge. So Coulomb is to electrical charge as a liter is to volume, as a kilogram is to mass. Coulomb is just a measure of quantity of electrical charge. So this thing is making noise. Hello. All right. They've got it turned up. See, a big mouth like me is not supposed to use this, I suppose, because when I put it up here, it's so loud. Maybe I should talk softer. All right. So if we then divide both sides of this equation by minus NF minus NF minus NF, we get the wonderful and always exciting Nernst equation. And that makes it make noise. Try it. And that equation is, so we just take that equation which we know all about, and we divide both sides by both sides of the equation by NF. We get Ecell is E0 cell minus RT over NF natural log Q. Now again, what is Q? Q is, if we're going back to that copper and zinc Daniel's cell, Q expresses the concentration of copper that you used in your cell and the concentration of zinc that you used in your cell. So this is why I say it's so useful that you can calculate the voltage of any cell. You make your cell, you decide what the concentration of copper or zinc or iron or whatever, and that's Q. Once you know that, you know E0 cell, you can look that up in a table, you can calculate E cell. So that's the power of this equation. Now I want to take an example, and you know, one other thing. Let's do this. RT over NF. Those are all constants. Yes?
So does that mean that the units for E cell will also be joules over negative NF?
Everything turns out to be volts. If you do a dimensional analysis, I'll just do one of them. So we got delta G. Everything turns out to be volts. So we got delta G in joules per mole, right? I went through this last time. Divided by N, that's moles of electrons per mole. F, coulombs per mole of electrons. So we get moles, electrons cancel, moles, electrons, moles, moles. You're left with units of joules per coulomb, and a joule per coulomb is a volt. So that's how you get from, by divide, so that's the key to this little dividing by NF. It's a good question. Why am I dividing by minus NF? Dividing by minus NF because, as I just showed you, it converts joules per mole into volts. And that's literally what, it's more than just math. That is conceptually what the voltaic cell does. What I just illustrated there is conceptually what the voltaic cell does. It takes the free energy change of the reaction in joules per mole and converts it to volts. And now you know how it does that. It divides by minus NF on all sides. Now, everything's got to have units of volts, including the RT over NF. Now, if we throw in all those constants, we already got the Faraday constant. It's the 8.3 joules per mole Kelvin. I think it's 8.3. I don't remember. We give you that constant. If we assume T is 298K, so now I'm going to take that term right up there, RT over NF. I know what F is. It's 9647 coulombs per mole of electrons. I know what R is. These are all constants. If I'm assuming room temperature, I'm running this cell at room temperature, I plug in 298K, and that gives us Nernst's magic number, as I like to call it. So we take the Nernst equation from our friend Walther Nernst. Our Nernst equation says Ecell is E0 cell minus RT over NF log of Q, where again, Q is whatever the components, concentrations, pressures, whatever you decide, that's what goes into Q. Now, if we plug in RT over NF, we get and convert to base 10 logs. So I like to call this that 0.0592 I call that Nernst, N-E-R-N-S-T, Nernst's magic number. Now, it's Nernst's magic number, one, because it comes right out of the Nernst equation. Two, it makes your calculations a lot easier if you remember Nernst's magic number. Because the bunching RT over NF, or NF over RT, comes up a lot in electrochemistry. So that bunching, RT over NF that you see up there, you see that a lot. So if you're encountering a problem that has RT over NF in it, you can do that calculation, multiply R by T, divide it by F, and you'll get Nernst's magic number. But it's much easier just to remember Nernst's magic number. So for me, this number is etched in my brain. I've been using it since I was an undergraduate. And it just makes it easy because then you don't have to do the math anymore. Every time you encounter a problem like this, you don't need to multiply R by T and divide by F. And also it converts, note very importantly, it's easier for us to think about base 10 logs, so I converted it to base 10 logs when I put in the constants. So Nernst's magic number, a good number to remember. So I want to take you through how I use the Nernst equation. So I use the Nernst equation this way. Let's say I assemble this cell. Let me make sure I get it right here. Yeah. I assemble this cell. It's a Daniels cell, Daniels type cell. So I got a zinc anode, and I got zinc 2 plus at 10 to the minus 3 molar. I got my salt bridge. And then I got copper 2 plus at 10 to the minus 2 molar. And then I got my copper. Now, first thing to note, these are not standard state conditions. Standard state would have all those concentrations at 1 molar. So this is not E0 cell anymore. This is E cell, which you must calculate using the Nernst equation. So the way I do this is to break it up into half reactions. Now that's not essential. You could treat it in an overall fashion if you wanted to, but I find it much easier to break it into the 2-component half reactions. So first I'll consider the cathode. So you will encounter problems like this. We didn't get this far for exam 3. So this would ordinarily be on exam 3, I guess because of the hurricanes and other problems this semester we got behind. But so this will be on the final, calculating the cell potential using the Nernst equation. So let's start with the cathode. I know my cathode half reaction is this one. And I'm going to write the Nernst equation for that half reaction. So that's going to be E for the cathode is the E0 for that process minus 0.0592 over N2 now log 1 over the concentration of copper. Why 1 over the concentration of copper? Because that's log Q. So if you write Q for that reaction, you have no concentration term for the copper because that is a pure solid phase. You do have a concentration term for the reactant, the copper 2 plus, and it's given there. So and then of course we know N is 2 because it's there right in front of us. Now, so then all I got to do is plug in my 10 to minus 2 molar into there, and I go to the old table of E0 values, and I find out that E0, so that's from a table of E0 values, and I get from the half reaction the copper concentration I got from the cell notation. And when I do that math, I get E cathode equals 0.281 volts. So you see what I did here? I used the Nernst equation in the half reaction form. I took each reaction. I'm going to do the same now for the anode reaction. So there's my cathode reaction. Do the same for the anode reaction. I'm going to write it as a reduction. So again, it is wise to write the reactions as reductions. Why? Because the E0 value assumes that. And so then I can write the Nernst equation for that. E anode is E0 for that reaction, minus 0.0592, Nernst's magic number, divided by 2, because again, n equal 2. And again, log. Now we're going to write the Q expression for this reaction. Again, we have a pure solid phase as the product. No concentration term for that. And then we've got this aqueous zinc 2+ solution. So I go to the handy-dandy table and I find the E0, and I find that that is minus, we already showed this number, 0.76 volts. That's that E0. In the cell notation, that was given as 10 to minus 3 molar. So that allows me to calculate, plugging in those numbers, E anode equal minus 0.849 volts. Now again, that negative sign only tells you that you wrote the anode reaction as a reduction, and it's not occurring as a reduction. No problem, because we take care of that negative sign this way. We write Ecell finally is E cathode minus E anode and I plug in my two values. I calculated Ecell was E cathode 0.281 volts minus my E anode 0.849 volts, and I come up with Ecell is 1.13 volts. So again, you'll have problems that ask you to calculate cell voltage using the Nernst equation. The approach I take is shown here. Take the cathode reaction, use the Nernst equation on it, calculate the voltage of the cathode. Take the anode reaction, use the Nernst equation on it, calculate the voltage of the anode. And finally, E cell is simply E cathode minus E anode. And there are variants of this. For example, we could give you the Ecell and ask you to calculate N. So there are various ways. Or we could give you Ecell and only one E0 and ask you to calculate the other E0. So there are lots of ways to work this, but the simplest way to think about it is calculating Ecell. Okay. So that's the general strategy using the Nernst equation to calculate the cell voltage. Now, let's get to the task then of balancing redox reactions. So, we've gotten by so far by considering pretty simple reactions, pretty simple half reactions, just about the simplest half reaction you could imagine. Or we considered half reactions like this. But they're simple. Simple because there's only two, in each of those half reactions, there's only two chemical substances in each reaction. And so balancing such reactions is easy. And you can sort of do it intuitively. But with some redox reactions, there are many, many more chemicals involved in the reaction. Sulfates and waters and oxygens and hydronium ions and hydroxides. And nevertheless, we have to balance those redox reactions. And what that means is, when we balance a chemical reaction, we know that, let's take my favorite reaction, N2 plus 3H2 goes to 2NH3. When you learn to balance a chemical reaction in high school, you said, okay, the number one thing is, if there are two nitrogens on the left, then there better be two nitrogens on the right. And if there are 6 hydrogens on the left, there better be 6 hydrogens on the right. So you learned that a very long time ago. It is the same for balancing, we'll call these in electrochemical cells, there's a name given for so now what we want to do is balance reactions occurring in an electrochemical cell. And what reactions are occurring in an electrochemical cell? Well, there's a reduction reaction, and there's an oxidation reaction. So these types of reactions that occur in electrochemical cells are sometimes called redox reactions. So that's a generic term for any reaction that would occur in an electrochemical cell. The cathode reaction is a redox reaction. The anode reaction is a redox reaction. We had that table of E0s up there with all those dozens and dozens and dozens and dozens of E0s. Those are redox reactions. So a general term for a reaction that occurs in electrochemical cells is a redox reaction. Now, just as in this conventional reaction, we got to worry about that same idea. If there's 2 sulfurs on the right, there's got to be 2 sulfurs on the left. If there are 6 oxygens on the right, there has to be 6 oxygens on the left. So we've got to conserve mass, just like when we learned to balance chemical reactions. But we've also got to conserve charge. And that's what makes balancing redox reactions unique. If the and why is there charge? Well, we know that there are electrons in redox reactions, right? All redox reactions. And so at the end of the process, this charge on one side of the equation has to be the same as the charge on the other. We can take a simple example. These two up here illustrate that idea very well. Let's take the right side. There's no charge, right? Left side, there's a 2+ charge, and there are 2 electrons. No net charge. So that's balanced. Same deal here. On the right, 2+. On the left, 3+ plus an electron, net 2+. So this is the unique feature of a balanced redox reaction. Not only do we have to balance mass, as we learn for any chemical reaction, but charge has to balance. Whatever the net charge over here is, that same charge has to be over here, or the reaction is not balanced. So you can't lose mass or gain mass, and you can't lose or gain charge. So now, your book gives I think it's a 7-step procedure for balancing redox reactions. I would follow this 7-step procedure. When I was in graduate school, I was an electrochemistry graduate student, and I thought, I don't have to follow any rules. I can balance redox reactions. I'll just, manipulate it. It looks like one too many oxygens. How about I put a water over here? Now I got too many hydrogens. Well, I can put a hydrogen here. Oops, now the charge doesn't balance. Okay, how about I throw 3 electrons over here? So that's called finessing it. And that's what I thought I could do. But after failing to finesse balancing redox reactions, I finally decided to follow the rules given in freshman chemistry. And when I have to balance redox reactions, which I do a lot, I follow the rules given in the freshman chemistry book. So this is one place, perhaps, where I'll say what the book is doing is really good. So let's walk through that and learn how the book tells us to balance redox reactions. So step one we'll give to you. Step 1 says, write the unbalanced. Sometimes it's using the term skeletal. Skeletal? So it's unbalanced. Is that how you spell skeletal?
You're forgetting an E after the L.
Huh?
Skeletal, there's another E.
Where?
After the L.
Really?
In the middle.
You can see how bad my spelling. You say, see, you didn't tell me which L to put it after. I'm looking at that going, that can't possibly be right. Skeletal, like a skeleton.
Yes.
So sometimes the unbalanced redox reaction is called the skeletal reaction. But we'll give that to you. So there you go. So here's a redox reaction that I'm going to balance. It involves copper. It involves nitrate. It involves copper 2+, and it involves NO2 gas. So obviously, it's not as simple as these ones that we have been pursuing so far. Now, so step 2 says break this into 2 half reactions. And, you know, this takes a little bit of skill, and you gain that skill by balancing redox reaction homework problems. So this takes a little bit of finesse, but this one's pretty easy, right? Because you see copper over here on the left, and you see copper over here on the right, so you, fine, that looks pretty easy. I'll just say there's one of them. Copper solid goes to copper 2 plus aqueous. And while I know it's not, now that one seems to be, at least in terms of mass, balanced. Now the other one's a little more complicated, but I can see that I've got an oxide of nitrogen here and an oxide of nitrogen there. So I'll just write, well, I'm not sure about this one, but it seems to be NO3 minus aqueous goes to NO2 gas. Now, step 3 is easy for this one. Step 3, very important. Balance all atoms except H and O. So now we're getting to the part of balancing the reaction, same as in chemical reactions. We want to conserve mass. But that conservation of mass is going to be in 2 steps. Because we're dealing with aqueous solutions, oxygen and hydrogen are unique players. Say that again. Because we're dealing with aqueous solutions, oxygen and hydrogen are unique players, and we're going to get to those unique players next. Let's take the simple ones. It says balance all atoms except hydrogen and oxygen. So let's take our 2 reactions. Copper solid goes to copper 2 plus aqueous. That's balanced. I don't need to worry about that. 1 copper, 1 copper. So this problem's easy. Check. No problem. Let's take the other one. So again, step 3 says balance all atoms other than hydrogen and oxygen. So the only thing I got here is nitrogen. One of those and one of those. So this also is pretty easy because other than oxygen and hydrogen, these 2 are already balanced. So step 3 in this problem, easy. Step 4, so step 4 says add H2O, H plus, and or OH minus to get H and O to balance in each reaction. Okay, let's take the nitrogen one first. We take a look at the nitrogen one, and we see nitrate going to NO2 gas. And so we see we got a problem with oxygen here, because we've got 3 oxygens on the left and we only got 2 on the right. But the rule says we can add water. Fine, I'll add water. Ooh, now I'm good with regard to oxygen, aren't I? 3 oxygens on the left. 1, 2, 3 oxygens on the right. But I got a problem here. I got no hydrogens on the left. So it says I can add H plus or OH minus. Now, a big clue will be given to you when you read the problem. It might say assume an acidic solution, or it might say assume a basic solution. Now there's a big clue, because if it's an acidic solution, it means there's a whole bunch of hydronium ion in the solution. So if you need a hydronium ion, it's there. If the problem says it's a basic solution, that means there's a whole bunch of hydroxide ions. So if you need oxygen and hydrogens in a basic solution, hydroxide might be your source. But let's assume we're in a basic solution and we need 2 hydronium ions. I'm sorry, an acidic solution, so I'm just going to throw them in there. There they are. So, step 4, add water or hydronium ion or hydroxide ion to get oxygens and hydrogens to balance. I got oxygen to balance by adding a water over here, but that created a problem with regard to hydrogens, so I put 2 hydronium ions over here. So now this reaction is balanced in terms of all of the mass. Let's take our other reaction. It's really easy. There is nothing else. So our other reaction is copper goes to copper 2 plus. This is a really easy one. Don't need to worry about it. There is no hydrogen, there is no oxygen, there's only copper. So again, this is a particularly easy example. Now, step 5. So far what we've done, yes?
What about the charges?
What we're getting next. Step 5, so far what we've done is balance mass. Now we got to balance charge. And so that's what step 5 says. It says, add electrons. To one side of each equation to get charge to balance. So we look at this one. It's real simple. Boom, done. No net charge on the left, no net charge on the right. Done. Now, for the other one, we look at this thing and we see that on the right we have no charge. Water neutral, NO2 neutral. On the other hand, on the left, oh, did I get, wait a minute. Oh, on the left, what have I got? 2H plus, 2 positive charges, 1 negative charge. So I'm going to add 1 electron to the left. So now that criterion is satisfied. We got 2 reactions two half reactions that are balanced in terms of mass and balanced in terms of charge. That's the whole point here. Balanced mass, balanced charge. Now, step 6 says we got to get the N values the same. Sometimes both. So final step is I want to add these two reactions together, but the problem is that the number of electrons is not the same. This reaction involves 2 electrons. This reaction involves only 1 electron. No problem. I'm just going to balance the first, multiply the first reaction by 2. So I'm just going to take this whole reaction here to get the electrons the same. Take that whole reaction and multiply both sides by 2. So if I do that, I get, I'm going to move the electrons over. I'm going to get 2 nitrates plus 4H plus plus 2 electrons gives you an NO2 gas plus a water. Oh, sorry, 2 NO2 gases plus 2 waters. So all I did was I multiplied that whole reaction by 2, and I did that to get the electrons to be 2, and there it is, 2 electrons. Now I take my other one, and step 7 says, add, no, it's the last part of step 6, add them together. We're done. Add them together. First thing to note, if you do this right, electrons cancel. 2 electrons on the left, 2 electrons on the right. And so now here is our balanced reaction. Just going to add this together. There's my copper solid, plus my 2NO3 minus, those were aqueous, plus my 4H plus aqueous, goes to copper 2 plus aqueous, plus 2NO2 gas, plus 2H2O liquid. And then finally, you can check it. The way I check the problem, that would be my step 7. So that's all step 6. Step 7 is check. Check, please. And here's how we check. We just put left and right, and then we list all of our atoms. We got copper. We got nitrogen, we got oxygen, we got hydrogen, and we got charge. But copper, if you look, I got 1 copper on the left, 1 copper on the right. 2 nitrogens on the left, 2 nitrogens on the right. 6 oxygens on the left, 6 oxygens on the right. 4 hydrogens on the left, 4 hydrogens on the right. And in terms of charge, if you look at it, 2 plus on the left, 4 H pluses plus 2 NO3 minuses, 2 plus on the right. So charge left, 2 plus, right, 2 plus. Balanced, you're done. All right, that's where I'm stopping. Have a nice Thanksgiving. Don't eat too much.